In this video, we're going to look at trigonometric graphs. We're going to cover the shapes of the graphs and how to use them to solve problems. The three graphs you need to know are y equals sine of x, y equals cos of x, and y equals tan of x. And we're going to begin with sine. You could be asked in an exam to sketch out these graphs, usually for values of x between 0 and 360. So let's have a look at the shapes of the graphs and how you might sketch them. We'll begin by drawing the x-axis from 0 degrees all the way to 360 degrees. Now you wouldn't need to mark on all of these points, just the key ones, and I'll come to that in a moment. Then we need a y-axis that goes like this, and I'm going to add some grid lines to make this easier to see. The graph of sine of x has a maximum value of positive 1 and a minimum value of negative 1, so I'm going to add those onto my y-axis. And the graph takes this shape. It starts at 0, 0, it comes up, and at 90 it reaches its peak at 1, comes back down through 180 at 0, at 270 it hits negative 1, and then comes back to 0 at 360. So the key points that you would need to mark on if you sketch this graph are this one here at 0, 0, this one here at 91, this one here at 180, 0, this one is at 270, negative 1, and this one here at 360, 0. You might recognize some of these from your knowledge of exact trig values. This point 0, 0 tells us that sine of 0 equals 0, which is something you need to know. The next point tells us that sine of 90 is equal to 1, another one that you need to memorize. Then we know that sine of 180 is 0, sine of 270 is negative 1, and sine of 360 is 0. So this is the shape of the graph of y equals sine of x. If you look closely, you can see the other exact trig values that you need to memorize. So sine of 30 is equal to 1/2, or 0.5. Sine of 45 is square root 2 over 2, which is a little bit more than 0.7. And sine of 60 is square root 3 over 2. So this is the graph of y equals sine of x. Now let's have a look at y equals cos of x. So for cos of x, we actually start up at positive 1. We come down through the axis at 90, we hit the lowest point at 180, we come back through the axis at 270, and then reach the top again at 360. So the key coordinates for this one are this one here, 0, 1, this one here, 90, 0, this one, which is 180, negative 1, this one is 270, 0, and the final one, 360, 1. So we can also see some exact trig values again. You should recall that cos of 0 equals 1, and that's confirmed by the point 0, 1. Cos of 90 is equal to 0, cos of 180 is negative 1, cos of 270 is also 0, and cos of 360 is also 1. We can also spot those other exact trig values, so cos of 30 is square root 3 over 2, cos of 45 was square root 2 over 2, and cos of 60 equals 0.5, or 1/2. The graphs of y equals sine of x and y equals cos of x are very similar. In fact, they have exactly the same shape, it's just been translated across by 90 degrees. If I draw the graph of y equals sine of x on top of this one, you can see they make exactly the same shape. If I move the sine of x graph to the left 90 degrees, it will actually map perfectly onto the graph of y equals cos of x. The graph of y equals tan of x, however, is a little bit different. Let's have a look at that one now. So for the graph of y equals tan of x, we'll do the same x-axis from 0 to 360, but the y-axis will be quite different. So this time it doesn't just go between 1 and negative 1. In fact, the graph of y equals tan of x can take any possible y value. So I'm going to scale this one from negative 10 to 10, but it could go all the way up to any possible number, and all the way down to any possible number as well. Now if you think back to when you learnt exact trig values, you might recall that tan of 90 is not possible to do. In fact, we said that tan of 90 was undefined. This means we can't plot a point at 90 degrees on this graph. Instead, we draw this dotted line here. This dotted line has a special name, and we call it an asymptote. It's a line that the graph is going to get closer and closer to, but never actually reach. Tan of 270 is also undefined, so there's a second asymptote here as well. Now that we've added these asymptotes, we can draw the curve. So it starts at 0, 0, and then approaches this asymptote like this. Then at the bottom we come away from that asymptote and make the same sort of shape but up to 180, and then go through that towards the second asymptote. And then we have the same shape that we drew from 90 to 180 between 270 and 360. So the graph of y equals tan of x looks like this. You can see it's very different to the shapes of the graphs for sine and cos. So what are the key points for this graph? Well, we've got 0, 0 here. We've got the asymptote at 90, of course. We've got this point here at 180, 0. Then we've got the second asymptote, and then we've also got this point at 360, 0. And this can help us remember that tan of 0 is equal to 0. So is tan of 180, and so is tan of 360. So we now know the shapes of the graphs of y equals sine, cos, and tan. But we've only looked at these for x values between 0 and 360, but that's not the whole story. Now let's return to the graph of y equals sine of x again, for x values between 0 and 360, and it looked like this. Now this graph actually repeats itself, going up and down in this wave shape over and over and over again. In fact, it goes infinitely in this direction. So there is no endpoint to this graph. And the same thing happens in the opposite direction as well. So not only does the graph repeat in this same way going to the right, but it also repeats in the same way going to the left, so into the negative x values. The first complete wave that we drew occurs between 0 and 360 degrees, so that's a length of 360. This length applies all the way across the graph, and you could call it its wavelength. So the second of these waves also has a length of 360, which means we can mark on this point at the end by doing 360 plus 360, which is 720. The same thing happens if we go towards those negative numbers. This must have a length of 360. So we go 360 backwards from 0, which is negative 360. We say that any graph that repeats in this way is periodic. And the period was the length it took to repeat itself, which in this case was 360 degrees. Now let's do a similar look at cos of x and tan of x. So the graph of y equals cos of x looks like this from 0 to 360. This wave will repeat every 360 in both directions. So going to the right, another 360 would be 720, we'll get another copy of this wave. And going in the negative direction to negative 360, we'll get another copy again. So this graph is also periodic, and its period is also 360 degrees. We can confirm the period is 360 by seeing that this wave here has a length of 360. This isn't the only place you could find the period of the graph. In fact, you could take any point and see the distance to the next corresponding point. So we could do it at the bottom of the graph here. This would also be 360. Or it could be done here, where it crosses the axis. This is also 360. So that's the graph of cos, but what about tan? So let's take the graph of tan of x from 0 to 360 again. We need two asymptotes, and the graph looks like this. Once again, this graph will repeat infinitely in both directions. So between 360 and 720, we'll get another copy of this graph. So we'll have those two asymptotes again, and the graph will continue like this. It also repeats in the negative direction, so if we go down one more cycle to negative 360, the graph will look like this. So since the tan graph continues to repeat, it is also periodic, but its period is not 360. If we check the distance between these 2 points here, it's actually 180, and you could do that between any two corresponding points or even two asymptotes. So the period of the tan graph is not 360, but 180. Now we're going to have a look at how you can use these graphs to solve equations. Sometimes in an exam question, they'll give you the graph drawn, and they'll ask you to solve an equation, like this one here. So we need to use the graph to find estimates for the solutions of sine of x equals 0.6, for x between 0 and 360. For this equation, we want to know the x values that give you a y value of 0.6. At the minute, we can't see 0.6 on the y-axis, so we're going to mark on the scale. Going between 0 and 1, there are 5 squares, so each square must be worth 0.2. So it goes 0.2, 0.4, 0.6, 0.8. So we now know where 0.6 is. If we draw a horizontal line at 0.6, we can see it crosses the graph of sine of x in two places. These two places represent the solutions to that equation. If we draw down from these intersection points to the x-axis, we see there are two x values where these graphs meet. These two x values are the solutions to the equation, since if you did sine of those values, you would get 0.6. Let's take a closer look at the graph to try and work out what those x values are. You can see that going between 0 and 90, there are 3 big squares, so each square must be 30 degrees. So we've got 30, 60, and then between 90 and 180, we've also got 120 and 150. Then going between each of the larger squares, we've got 5 smaller squares, and they cover 30 degrees, so 30 divided by 5 is 6. So each small square is 6 degrees. So we have one solution that's one square past 30, so that solution will be 36. We've also got a second solution which is one square before 150, So if you do 150 take away 6, you find the second solution is x equals 144. So these are the two estimates for solutions of that equation. Let's try another example. So for this one, we're going to use the graph to find estimates of sine of x equals negative 0.9. This time then, we're looking for the graph to give us values of negative 0.9. So if we add on the scale at the bottom, negative 0.2, 4, 6, and 8, and we want to draw a horizontal line at negative 0.9, you can see there are still two places where this graph crosses. So if we draw lines back to the x-axis, we can see there are two values that we need to find. This time it's 1 square past 240, so 246, and then 1 square before 300, so 294. Let's have a look at a similar question but using the graph of cos of x. So this time we're going to solve cos of x equals 0.3. So we need to draw a horizontal line at 0.3 on the y-axis, that goes here, and you can see the graph crosses in two places, so these are the two solutions we're after. This is using the same scale as before, so one small square represents 6 degrees. So we need to look 2 squares past 60, which would be 72 degrees, and then 2 squares before 300, so that will be 288 degrees. And also we're going to solve the equation cos of x equals negative 0.4. So we draw a horizontal line at negative 0.4, and then go back to the x-axis, and these are our two solutions. So 1 square before 120 is 114, and 1 square past 240 is 246. Sometimes we need to use the graphs to solve equations, but they're not drawn on graph paper, and they're just given as a sketch like this one here. For this question, they might mark a value on the x-axis, for example 37 degrees, and tell us the corresponding y value, but in this case they're just going to write k. And the question might read as follows: sine of a equals k, where a is in between 90 and 360, and we need to find the value of a. Now this is quite a wordy question, but it's not actually too difficult to do. We've been given sine of a equals k, where a is just some value. Now we know that a could be 37, because from the graph we can see that if we did sine of 37, we would get k, so sine of 37 equals k. But if you look at this inequality here, we've been told that a must be between 90 and 360, and 37 is not, so that's not an acceptable answer. So we're looking for another value that we can input into the sine function to get the same k value out. If you continue the horizontal line from k across, you can see we hit the graph in a second place. And it's this value here that we want to find, because it will also give you the value k if you do sine of it. So this must be our value of a. Now you can find the value of a even though this hasn't been drawn on graph paper. To do this, we're going to use a symmetry property of the graph. This graph is symmetrical about this line here, so everything on the right is a reflection of everything on the left. We know the horizontal distance from the origin to 37 here is 37, since 0 plus 37 is 37. This must therefore be the same distance from 180 back to the value we're trying to find. So if we do 180 subtract 37, we'll find the value of a. So for the answer for this one, all we would need to do is 180 take away 37, which gives you the value of 143 degrees. There could be a second part to this question. They could say sine of b and sine of c both equal negative k, where both b and c are between 180 and 360. And we're told that b is less than c, and we need to find the values of b and c. So this time, rather than sine of a number being equal to k is equal to negative k, well we know where k is on the y-axis, so negative k must be the same distance below 0, so negative k will be somewhere down here. So if we draw a horizontal line across, we can see this crosses the graph in two places, here and here. So these must be the values of b and c. And we can see from the inequalities we're told b and c are in between 180 and 360, and we can see from the graph that these two are. We're also told that b is less than c, so this means the one on the left must be b, and the one on the right must be c. So how do we go about finding these values? Well, once again we can use the same symmetry properties. To get from 180 to b must be a distance of 37, and it must also be a distance of 37 to get from 360 back to c. So we can work out b by doing 180 plus 37, which is 217, and we can work out c by doing 360 subtract 37, which is 323. Let's have a look at another example like this one, this time using the graph of cos of x. So a value is marked onto the graph at 52, and we're told that this gives you the value of k when we do cos of it. The question says cos of a equals k, where a is in between 270 and 360 this time. and we need to find the value of a. So just like before, we're looking for the value of a that we could put into cos to get k out. And we know that cos of 52 is k, but we need an answer between 270 and 360. So if we extend our horizontal line across from k, and then go down, this is the value we're after. So this is the a value, and you can see it is between 270 and 360. So how would we work this one out? Well, the cos graph is also symmetrical. We could draw a line of symmetry down here. To get from 0 to 52, we add on 52. So this must be the same distance as going from 360 back to a. So that's also 52. So to find the value of a, we do 360 subtract 52, which is 308. Now let's try a second part to this question. So we've got cos of b and cos of c being negative k, and we've got these inequalities again. We're told that b is in between 90 and 270, and so is c, and b is less than c, and we need to find their values. So just like before on the sine one, we're going to mark on negative k, and draw a horizontal line, and you can see the two solutions here. So these must be the values of b and c. And since b is less than c, we know that b is the one on the left, and c is the one on the right. This time, the distance from 180 back to b is 52, and the distance from 180 up to c is also 52. So to get the two solutions, we need to do 180, subtract 52 for b, which gives you 128, and for c, we need to do 180 plus 52, which is 232. Now we're going to look at an extension to this question. What if instead we were told that cos of m equals k, and m is between 360 and 720, and we've been asked to find the lowest possible value of m? Well, this time m is between 360 and 720, and we can't see that on our graph. But we do know that cos is a periodic graph and repeats itself every 360. So we could draw in a second cycle of cos, and it would look something like this. So since we're finding cos of m equals k, we can extend that horizontal line from k, and we can see there are more solutions. In fact, there are 3 more here that we don't know. But since we know that m is between 360 and 720, we're only looking for where it crosses the green part of the graph this time. So these are 2 possible values here. But the question does say to find the lowest possible value of m. So we're only interested in the lowest possible solution, which would be this one here. So we just need to work out what this value of m would be. Now there are 2 ways that you could do this. We could draw a dotted line down through 360 like this, and the distance between 0 and 52 must be the same as the distance between 360 and m, so 52. So we could just do 360 plus 52. Alternatively, we could use the property that these graphs repeat every 360 degrees. So we know the first solution on the left at 52 must be 360 degrees before this next solution, since they're at the same point on the downwards part of the curve. So the distance between here and here must be 360. So we could just do 52 plus 360. So either way, you'll end up with the answer 360 plus 52, which is 412. For our final question, we're going to look at how you can do the same sort of process with the graph of tan. And just like in everything we looked at before, tan is ever so slightly different. So for this question, they're going to mark on a value, in this case it's 70, and we're going to be told that tan of 70 is equal to k. And we're going to solve tan of a equals k, where a is between 180 and 360, and we need to find its value. So just like in the previous 2 examples, we're going to extend this horizontal line from k until we hit the graph again. And this must be our value of a. And this is good because it is between 180 and 360 like the question says. So how do we find this value for tan? Well, tan is actually quite easy to deal with. Because it has a period of 180 and the graph looks like this, we can just add or subtract multiples of 180 to find the next solution. So the distance between 70 and the next solution here is just 180. So to find this value of a, we could do 70 plus 180, which is 250 degrees. So a is 250. And let's have a look at a second part to this question. So we've got tan of b and c being equal to negative k, and we're told here that b is between 90 and 180 and c is between 270 and 360, and we want to find their values. Well, just like before, we're going to mark on negative k onto the axis, and then draw a horizontal line and see where it hits the graph. And you can see there are 2 places where it hits the graph here. In this one, we're told that b is between 90 and 180 and c is between 270 and 360, so we can be confident that b is the one on the left and c is the one on the right. So how do we find these? Well, this time we don't know any of the solutions, but we can use a symmetry property again. To get from here to here is a distance of 70, and that's the same as the distance from 180 back to our solution of b. So to find the value of b, we do 180, take away 70, which is 110. To find the value of c, we have 2 options. We could also subtract 70 from 360, or we could use the fact that we know that there's a 180 period between the values of b and c. So to get the value of c, we could do whatever b was and add 180. So we could do 110 plus 180, which is 290. Thank you for watching this video, I hope you found it useful. Check out what I think you should watch next, subscribe so you don't miss out on future videos, and why not try the exam questions in this video's description.